Hello everyone, this is Mrs. Gunlock and this is my assistant. And this is Chapter 3, Part 2 of 2, in which we discuss the finer points of stoichiometry. Stoichiometry is what allows you to get from amount of reactants to amount of products so that you can figure out, hey, if I start with this much, how much will I end up with? And this is kind of the very mathy part of chemistry. And we did a whole bunch of this last year in regular chemistry, but we're going to do more of it with more numbers this year in AP chemistry. So here is kind of a rundown of the basic structure of how to do it. Dimensional analysis is the name of the math that you use to do stoichiometry, and there's several things you need to remember about dimensional analysis. One is that your units are very crucial, which means that if you start writing a bunch of numbers with no units, you will get lost. I demand complete units, and you will lose points if you do not put them. So, for example, this here is a molar mass equality, and what it does is it makes a true statement about the molar mass of something. So what this is saying is that, hey, every time you've got 1 mole of carbon, you have 12.01 grams of carbon. They're the same thing. So they are equal. It ends up being a fraction where the bottom unit is canceled by the previous top unit, and the top unit cancels the next bottom unit. So you, when you're doing these problems, you go back and you check and go cancel, 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 cancel to make sure that your units cancel. But what if I don't put units? Well, then you will have no idea if you did it right, because the only way to know if it's right is if your units cancel and if your equalities are true. So that's your molar mass equality, and we talked about molar mass last time. Another equality is the definition of a mole equality, which is 1 mole of any kind of particles, 1 mole of anything, is the same as Avogadro's number of that thing. So 6.022 times 10 to the 23rd atoms is a mole of atoms. That is a true statement. If this was 2 moles of atoms, is 6.022 E23 atoms, that is untrue, and that is going to give you a bad answer. So that's important that, these equalities must be true statements. You must cancel the units. Another equality is the mole ratio equality. And what that's doing is relating in the reaction that I am working with, and apparently this reaction has carbon dioxide and oxygen in it. In this reaction that I'm working with, every time I use 3 moles of oxygen, I get out 2 moles of carbon dioxide. If you have not yet balanced your equation, you cannot make this, because the 3 and the 2 are the coefficients from the balanced equation. So typically, you have to make sure that either they gave you a balanced equation, or you took the equation and balanced it, or I gave you the thing in words and you have to write the equation and balance the equation and do the stoichiometry, and that's when I'm feeling mean. Another equality that we've encountered before is the volume of a single mole of gas at standard temperature and pressure, which it's important to remember what standard temperature and pressure is, because if the temperature is different or if the pressure is different, this is not true, and they have to be true. So standard temperature and pressure is 0 degrees Celsius, also known as 273 degrees Kelvin, and 1 atmosphere. And under those conditions, 1 mole of any gas, like hydrogen gas, H2, or chlorine gas, Cl2, or carbon dioxide gas, CO2, 1 mole of any gas takes up the volume 22.4 liters. Only if it's at STP. If it's not at STP, you have to go back and remember your gas equations like PV equals nRT and neener. But frequently they're nice to you and they say at STP blah 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 blah, and you go, hey, I can use this equality. And And then one equality that we haven't used super much, but that we will be using more when we get into stoichiometry that goes on in aqueous solutions, is the definition of molarity, which we've learned about molarity, which is that 1 mole per liter is 1 molar. But this one ends up getting used when they say, you are given 250 milliliters of 2 molar sodium chloride solution. Well, that's sort of confusing because it's got 2 numbers in it. So what do you start with? Do you start with the 250 milliliters or do you start with the 2 molar? You start with the amount of solution. So that would be 250 milliliters of solution over 1 times, then you bring down mils of solution, and you can use mils if you do 1,000. 1,000 mils of solution. And in 1,000 mils of solution, how many moles of sodium chloride are there?
1.
No.
Uh-oh.
Say 2.
2.
Yeah, because in the problem that I proposed a second ago, I said 250 mils of 2 molar sodium chloride solution. In that, there are 2 moles of sodium chloride in 1 liter of solution. So you end up putting the numbers from the question in the first slot and the second slot. And don't get them backwards, and don't just stick in ones.
No.
Assistant. All right. So we're going to run across that more in chapter 4 than in chapter 3. All right. So here is an example. Given the reaction below, how many grams of silver sulfide can be made using 3.94 grams of silver nitrate with excess sodium sulfide? It's important to notice excess. When they tell you that something is excess, they're being nice. That means that the number that you need to start with is the number given for silver nitrate, and we can ignore sodium sulfate. Sodium sulfide. And they're asking to get from grams of this to grams of this. And I will go and do that on the black screen. All right, so we start with what we have. We have 3.94 grams of silver nitrate. You put that over 1. Why do we put it over 1? Because if you don't, you keep thinking that it's on the bottom. And then that makes you sad later. You always multiply by some equality. And so you just go ahead and you go times a line. And then you always bring down your unit. So you go ahead and bring down your unit. This is before you even ask yourself, what am I doing? Now you ask yourself, what am I doing? You're trying to get from grams of this to grams of this. In order to do that, you're going to need to, what are you going to need to do? Balance your equation. It's a good point. Let's do that. Can I click? No. Yes. Yes. I need space to write numbers. All right, to balance the equation, we need to go and look at dudes that don't match. Sodium doesn't match. Where's my pen? All right, sodium doesn't match, so let's make a match. 2 moles of sodium nitrate will make the sodiums happy. And silver doesn't match. 2 moles of silver will make the silvers happy. Did that happen to make my polyatomics happy? 2 nitrates, 2 nitrates? Yes. 1 sulfur, 1 sulfur? Yes. Beautiful. Okay, so we'll need that in a minute. All right, so what we need to do is get from grams of this to grams of this. That's going to require this plan, grams to moles of the first compound, convert from moles of that compound to moles of the second compound, and then from those moles, get to grams of the second compound. In order to get from here to here, that's going to be your molar mass equality. Give me that M. You don't. your molar mass equality. And to get from moles to grams of this, that's your molar mass equality. To get from moles of the first compound to moles of the second compound, that is your mole ratio equality. Goodbye, R. And that is going to be the basic structure of our problem here. What do we know about grams of silver nitrate and getting to moles? Well, that's molar mass. 1 mole of silver nitrate, which I've already done this problem. And so you can check me and see if I'm right about the molar mass, which is 169.91 grams of silver nitrate. All right, so that accounts for the mass of it. This is our next step, which is moles to moles. Bring down your unit. And we need to get to moles of the other compound being silver sulfide. Do we have to write the whole unit out? Yes. But, Mom... All right, that's the relationship between these two compounds, is that every time you use 2 moles of this, you get 1 mole of this. So that's 2 moles of silver nitrate, resulting in 1 mole of silver sulfide. All right, just one more. Bring down your unit. And that's going to be molar mass again. So the molar mass of Ag2S, that's 1 mole, has a mass of some number of grams of it, which should make you happy because it says how many grams can be made. Well, this last unit here on the top, when you get to the unit that you're looking for, you are done, which means we're about to be done. And the molar mass that I have pre-calculated for silver sulfide is 247.86. Let me know if I'm wrong. We will delight in that.
Yes.
And so what you end up having is your units canceling. Grams of silver nitrate divided by grams of silver nitrate. Moles of silver nitrate divided by moles of silver nitrate. Moles of silver sulfide divided by moles of silver sulfide. This gives me good confidence that I did this right. I ended with the unit I wanted, I started with the unit that was given, and all of the intermediate units got canceled out, which means that the unit for my answer is grams of Ag2S. That makes me happy. And the answer for that is 2.87 grams of silver sulfide. Ta-da. The next part asks, what's the net ionic equation? Which is pretty great. We learned how to do this a little while ago. What you need to notice is that silver sulfide, nope. Sodium sulfide is aqueous. Silver nitrate is aqueous. Sodium nitrate is aqueous, but silver sulfide is a solid. This is a precipitate, so if you actually mixed these two suckers together, you'd get a little solid pile on the bottom of your beaker, and then this would be left in solution. So in order to do the net ionic equation, you cancel out the dudes that didn't do anything. Well, that's 2 sodium ions, a sulfide ion, 2 silver ions, those are cars, 2 nitrate ions. That gives you, and then here's the interesting part, because this is a solid, they're not floating around aqueously as ions in solution. There are little chunks at the bottom, so you leave him like that. But these guys, 2 sodium ions and 2 nitrate ions, are floating around as ions, and you cancel out the ones that are spectators, leaving you with sulfide and silver yields silver sulfide, which is frankly sort of obvious. I'm just saying. All All right, back to the notes. That was done when they've given you the information that one of them is excess. If they're mean to you, they'll say, you mix these two things. Let us know which one is excess. That's kind of sad. So sometimes there's way more of one reactant than you need for this reaction to finish. The one that runs out first determines when the reaction stops, and there will be leftovers of the other one. So this is like a cheese sandwich. If you have got 12 slices of bread and you're going to make a sandwich, that would indicate that you can make 6 sandwiches. It's a cheese sandwich, so we're going to go to cheese next. But if you have 5 pieces of cheese...
I don't like cheese.
Hush. That would indicate that you could make 5 sandwiches based on that amount of cheese. Can you make 6 sandwiches?
No.
No, because there's not enough
Cheese.
Good job. He's a very quick assistant. So that's the idea with the limiting reactant is, you've got 2 things, you use them at different rates. You're using bread at 2 slices per sandwich. You're using cheese at 1 slice per sandwich. And so, what do you run out of first? You ran out of the cheese first. Although it is possible in other circumstances to run out of the one that you have more of, but you're just using it so fast that you'd run out. So let's do it like that. Let's say you have 12 slices of bread. How many sandwiches could you make?
6.
Let's say you have 8 slices of cheese. How many sandwiches could you make?
8.
Very good. Which number was smaller? 12 or 8?
8.
Yeah. But how many sandwiches can you actually make?
8.
You can't make 8 sandwiches.
Oh.
You have 12 slices of bread.
Right. 6.
He's a good one.
I'm great.
Good assistant. All right, so limiting reactant problems ask you to calculate which one is which. You have to figure out who runs out first. So here's another example. I'm going to go do it on the black screen. Burp. Okay, so you react 10 grams of hydrogen with 50 grams of oxygen. Which reactant is limiting? Now, if you go with your first instinct and say, the small one, 10 grams of hydrogen, there's several things that you aren't taking into account, and so you cannot actually be sure that you're going to run out of hydrogen first. You're not taking into account the mass of the hydrogen, and you're not taking into account the rates at which you are using hydrogen and oxygen. So you got to do that. All right, first you have to balance your equation to figure out how fast you're using these guys. We need twice as much water here to account for the oxygens, and twice as much hydrogen to account for the hydrogens we just changed. So that's 2 to 1 to 2. That means that we use 2 of these, we use 1 of these, we get 2 of these. Now, what we need to figure out is how many sandwiches can we make with the hydrogen, and how many sandwiches can we make with the oxygen. Excuse me. So you do this grams to moles to grams thing twice. But twice is twice as much work. That's exactly correct. All right, so 10 grams of hydrogen. Don't do that. Bring your unit down. Do I have to write the whole unit? Yes. And we're going to moles, so 1 mole of hydrogen has a mass of 2.02 grams of hydrogen. Next, moles to moles. Moles of, what are we making? We're making water. And we are, what? No, I'm no good. Bring your unit down. Bring your unit down. That is 2 moles of hydrogen, and that's compared, to the moles of water, which is 2 moles of water. And then you bring your unit down, and that's moles of water, and we need to find out how many grams that is. And you may find that you actually end up memorizing the molar mass of water as 18.02, which gives us 89.16 grams of water. Now, here's something I noticed. If you mix 10 grams of hydrogen with 50 grams of oxygen, can you get out 89 grams of water?
Yes.
No.
Oh.
The law of conservation of mass says that we better be getting out something more like 60 grams of something, because
Right.
you can't have more. It's too much.
Fine.
Yep. All right, so that's that one. So I'm pretty sure that hydrogen is the one that is wrong, which means that it's in excess. But we're going to do this one too, because we love math.
We do?
50 grams of oxygen. Yes, we do love math. Mandatory love. This one is very similar in structure to the previous one, and that makes it easy to get it right, which means I'm probably going to get it wrong as you're watching and you can laugh at me.
Ha ha ha.
My assistant is kind of bizarre. In fact, one thing that's useful to notice is that the last half of limiting reactant problems, once you do the first one, it's the same. So that saves you a little bit of time. 56.28 grams. So what this is telling us is, if we used this plan and we started with 10 grams of hydrogen and it worked, we would be able to make 89.16 grams of water. If we started with 50 grams of oxygen and that worked, we would be able to make 56.28 grams of water. We cannot actually make 89.16 grams. We can make 56.28 grams, and we're going to leave a little bit of the hydrogen left over. So this is how much you can actually make. And the question, which reactant is limiting, is this guy here. Oxygen is the limiting reactant. Hydrogen is the excess reactant. Kind of don't want to switch back to the notes, do you?
Computer is haunted.
It's good. Okay. Percent yield and theoretical yield. In the real world, that's the lab. What if you went and did all of this, like for real, and actually reacted those two things together, 10 grams and 50 grams, and you were going, I'm going to make 56 grams, but then you got 48 grams?
Oops.
What does it mean? It means that you screwed it up.
Thank you.
The question is, how badly did you screw it up? That's always important to figure out. And that's why you look at your percent yield. So this is comparing your actual yield, which was 48, to your theoretical yield, which was 56 grams. Ha! You didn't notice that that was there and gave away the answer, did you? And so percents, which are always part over whole times 100, are going to give you 48 divided by 56 times 100, and that gives you, what does it give you? 86%. So that means you got 86% of what you expected to get. Is that good enough? It depends on who you are and what you want to accomplish. If this is like high school chemistry lab, your goal is probably something like, make some. Okay, well, woo, you did. You made some. If you are a professional chemist and you work for a company that sells water, they're going to call you in and say, so we noticed that your yield is only 86%. Have you been working to increase that? We want a better profit margin.
Okay.
So, it gives you a number as to how well you are doing, and then you got to figure out what you're going to do with that. So, percent yield. All right, now we have your favorite, some problems to do. Pause the video, and then do them, and then come back and see me do them. Welcome back, and here, oh, where's my pen? There it is. All right, and here we go. How many grams of water vapor can be generated from the combustion of 19 grams of ethanol C2H6O? You may have noticed that I am very mean.
Yes.
Not you. Because I didn't give you the formula. I didn't give you the equation. You're going to have to write it all by yourself. That means you're going to have to remember combustion, and that was from like February. All right, here it is. C2H6O is ethanol. You're combusting it. When you combust, you burn in oxygen. That gives you the result, carbon dioxide and water, if it's a complete combustion, but we're going to assume that it is. Ta-da! I wrote the formula, and now you have to balance it. Oh, it's so mean. All right, 2 carbon dioxides. We need to fix our hydrogens. And now we've got 4, 5, 6, 7 oxygens. There's one of them, so we need 6 here. 3. Bam. 1 to 3 to 2 to 3. All right. How many grams of water can be made from this? So from this compound, we need to get to water. And that's going to be grams to moles to moles to grams. So let's start. 19.0 grams of C2H6O. Bring down your unit. And that's equal to 1 mole of C2H6O. This is the molar mass equality. And I believe that the molar mass is 46.08. Then you need to get from this compound to this compound. Bring down your unit. And moles of water. That's going to be 1 mole of ethanol. Every time you do 1, you get 3 of those. That gives you, bring down your unit. Do we have to write the whole unit?
Yes.
Maybe. Oh, yes.
Be good.
And then grams of water is 18.02. That gave me the answer 29. But let's remember our sig figs from a couple lectures ago. We got 1, 2, 3 in the problem, so we need 3 here. So 22.3 grams of water can be made. Although this is sort of an inefficient way of making water out of booze. All right, second question. You may have noticed again that I am mean. A reaction combines 133.44 grams of lead 2 nitrate with 45.010 grams of sodium hydroxide. Which reactant is limiting excess? How much lead 2 hydroxide is actually formed? You didn't actually give us all the products. Yeah, but you can figure them out. You're smart. Oh.
Thank you.
Not you. All right, lead 2. That's your lead ion. Nitrate, I don't remember nitrate. It's NO3 minus. Now you're going to need to figure out the formula, which is PB parentheses NO3 2. All right, with sodium hydroxide, which maybe you actually remember is NaOH, and lead 2 hydroxide. I gave you one of them. Quit complaining. So what's left? The sodium and the nitrate. Okay. And balancey balance. We need a couple of nitrates. We need a couple of sodiums. And we have a couple of hydroxides. That's beautiful. Now you have a balanced equation, which means you can start the problem. All right. This is a limiting reactant problem, which means you get to do twice as much work starting now. These are really long. Yeah. 484. It's not going to help if you start deleting my decimals, Mr. Computer. Do we have to write the whole unit?
Yes.
Yes. Grams of lead nitrate. And then this is grams to moles to moles to grams. And I have calculated that this molar mass, I believe, is 331.22. And then moles to moles. What are we going to? Lead hydroxide. And that's 1 to 1. And then we need to get to grams again. And that is 241.22. That gives me 97.21 grams of lead hydroxide. Look at that. You're half done. Blurg.
Yay.
All right, and then 45.010 grams of NaOH. Which has a mass of 40.01. 1 mole of sodium hydroxide. And now the mole ratio. Turns out that comparing sodium hydroxide to lead hydroxide, every time you have 2 moles of sodium hydroxide, you get 1 mole of lead hydroxide. And now get that sucker into grams using the molar mass, which is still 241.22. You don't have to recalculate that. If you remember, the second half of these guys are always the same. And that gives us 135.72 grams of lead hydroxide. Now you can answer the question, which is which reactant is limiting or excess? Make sure that when they ask you which reactant is limiting or excess, you tell them a reactant and not a product. The answer is not lead hydroxide. That is not a reactant. But what we can see is that starting with this much lead nitrate, you can get 97 grams of lead hydroxide. Starting with this much sodium hydroxide, you could get 135 grams. How much can you actually get? The small number. So this is right, which means that the reactant that was limiting is the reactant that gave you this. So there is your limiting reactant, lead nitrate. Your excess reactant is sodium hydroxide. And the amount that you can actually make is 97.21 grams. And I probably need another decimal place because that's got 5 sig figs, but well, I don't know the next decimal place. You guys should have it though. All right. Okay, and then this question, if the actual yield of lead hydroxide were 80.02 grams, what was the percent yield? Well, that's part over whole, so 80.02 grams of lead. Do we have to write the whole unit?
No. Yes.
Over whatever, what was it? 97.21 grams of lead hydroxide times 100. You end up with 82.31%. Bam. Ta-da. The end. See you next time.